let m lambda, let lambda in Tc star and V lambda the corresponding Verma module, and m lambda the unique irreducible G module quotient. Then m lambda is finite dimensional if and only if two lambda alpha by alpha alpha is in non-negative integers for every alpha in delta, or for every alpha simple. That is the assertion. I gave a proof last time which is a little clumsy, and on top of that I am not sure the details work out right. So I will give a different proof this time. The initial steps are correct. First thing is to note, if we look at alpha simple and V not equal to 0, an eigenvector corresponding to lambda. Notice the corresponding eigenspace is one dimensional. So I pick this vector V and then I look at E minus alpha over k V, which I call Vk. Then one found that I proved this last time, and it's easy induction which does that. E alpha Vk equals Vk minus 1 into some constant depending on k, of course, some Ck times Vk minus 1. And one found that if k equals 2 lambda alpha by alpha alpha, then Ck Vk, then if k equals this, then Ck is 0. So, and then from this one deduces then that E alpha that Vk is actually 0. The point is, this is proved like this. You look at E beta, E minus, look at E beta of Vk. This is in the eigenspace of lambda minus k alpha plus beta. But this is not of the form, but every eigen character or weight, as call it, in V lambda is of the form lambda minus sigma m alpha alpha, so minus sign, alpha and pi, and m alpha greater than 0. So, everything is the form lambda minus. After all, we know that V lambda itself is what I call u minus, what did I call it, n or u, n I think. Yeah, it was the form u n minus of V lambda of V. I called it V, right. U n minus, so everything is the form u n minus V. If you look at elements coming from here, that will mean that you are looking at E minus alpha 1, E minus alpha 2, etc., E minus alpha k with all the alpha I positive applied to V. Then the eigenspace is going to be lambda minus alpha k minus etc. minus alpha 1, which is therefore the form lambda minus. If I write the simple roots, it will always be like this, but this is not like this, that form. This shows hence E beta Vk, hence Vk has to be 0. Yeah, let's see E beta Vk is 0 for every simple root including alpha, because for alpha it is by choice. So, beta and for every beta and pi. But if this happens, but you know in which case this implies u minus un minus Vk is a submodule of m lambda, which is assumed irreducible. Which implies un minus Vk is 0, which implies Vk is 0. You apply un minus Vk, you know on Vk all the simple roots applied are become 0. So, if you like, Ug of Vk is un minus times u Tc times un plus on Vk. Notice that un plus is 0 and this is an eigen Tc. Vk is an eigenvector for all of Tc, so the whole thing stays inside Cvk, and then you are applying un minus. So, un minus Vk is a submodule of m lambda, and that there m lambda being irreducible, it has no proper submodules. So, that implies Vk is 0. That implies the module, this is submodule, un minus Vk is submodule of lambda, and it's a proper submodule because it does not contain, notice that this does not contain V itself. So, unless of course it can, if it contains V, then un minus V is 0, which means the module itself is 0. If m lambda is not 0. So, all this goes on to show that if m lambda is 0, there is nothing to prove, it is one dimensional. If un minus Vk. So, yeah, in any case, if this happens, then you find that m lambda itself is 0, which is so since m lambda is a simple module which is not 0, we conclude that it's this condition holds. So, that all of which goes to show that E minus alpha power k, which is equal to 2 lambda alpha by alpha, V is 0 for every alpha in pi. For every simple root, the corresponding E minus alpha acts nilpotently on the vector V. Claim now is the following: E minus alpha acts nilpotently on all of m lambda. That is, I want to say E minus for every vector V in
still alpha is simple.
Sorry,
Still alpha is simple or not? Claim.
E minus alpha acts on all of m lambda is what I am saying.
No, but alpha is simple or not simple?
Simple. Alpha and pi. Yeah, alpha and pi. E minus alpha acts. The point is, I shouldn't say it acts nilpotently. It acts what is say locally nilpotently. What I mean by this acts, okay, acts locally nilpotently. By which I mean the following: that is, if W is any weight vector, then there exists n W alpha integer such that E alpha power n W alpha on the vector W is 0. Some power of E alpha will annihilate any given vector. The power may depend on the vector. That is why I do not want to call it nilpotent, because it depends on the vectors. That is why it is called locally nilpotent is the terminology usually used. So, how does one prove that? It is actually quite easy. The point is this: you look at the mapping UG tensor m lambda to m lambda given by, take any element x here and m lambda, this pair will go into x on m. Look at this map. Now, UG has a natural structure of a G module via the adjoint representation. That is, you look at any element x in UG and take any write x z in UG and take any x in G, then define, I will call it add x on z is by definition xz minus zx. Notice that by the definition of the enveloping algebra, each UP GC is a submodule. So, G submodule of UGC for this structure. This is the definition of the GC submodule. I call this, if you like, let me call it add u. Add ux, it operates on the whole of UGC, add ux. There is another structure, namely simply left multiplication by elements of G. I am not looking at the structure, I am looking at the adjoint structure, which is xz minus zx. The point is each UPGC is a GC submodule, because we know that in the analytic algebra we know that if you take x and y in the if you take take U2 for instance, take the product of two elements z1 z2 and I apply x, then what happens? It becomes bracket x z1 to z2 plus the bracket of x and z1 z2 is same as bracket of x z1 times z2 minus bracket of z1 x z2. Because of that you find that each that says that U2 GC is stable. So if z, so what do I bracket xy on z xy z minus z xy, expand it out, this is xy minus yx in the enveloping bracket yx to z minus z into xy minus yx. Expand it out and you find eventually you get the whole thing stays. If you take z in UPG, you find that the whole thing stays inside UPG. So what happens is this UPGC for this is a UGC submodule, and notice this is finite. UPGC is a finite dimensional. So UGC for this UGC module structure, it's actually a finite dimensional submodule. So finite dimensional GC submodule. Each UPGC is finite dimensional. So now if you look at this map, I claim that I said this is a GC module homomorphism, because you know what on the tensor product, how does it operate? If x is in G, C, x on something z tensor M by definition is going to be yeah, xz tensor M plus z tensor xm. That is how it is going to operate. If you, from this definition, it is quite easy to see that this is the definition of how x operates on z tensor, on the tensor product. It operates like this: add x z tensor M plus z tensor xm. And with this operation, you see that this, we know that UG is a sum of finite dimensional modules. And if you look at, this is the way it operates. Now look at, let V alpha denote the Z, denote the, what did I call it? I forget now. C alpha submodule of m lambda generated by the vector V. Then we know that alpha V is of is finite dimensional. In fact, of dimension 2 lambda alpha alpha plus 1. We came up to k, and then we found when I apply one more e minus alpha, it becomes 0. So, it is exactly lambda plus 2 lambda alpha by alpha alpha plus 1 dimensional module. And now you look at UG C tensor, this alpha v, tensor C of alpha v lambda. This tensor product clearly decomposes into a sum, not a direct sum of finite dimensional module, because UGC we have seen decomposes like that into a finite dimensional module, and this also decomposes into, this is already a finite dimensional module for SL2. So, this is a sum of finite dimensional SL2 modules. Now, look at its image, hence same holds for its image in m lambda. But this image in m lambda is whole of m lambda, because we know as a UGC module it is irreducible. Okay. See, this mapping is a G module homomorphism, and as m lambda is a irreducible G module. So, the image, this when you look at the image, it is the module generated by this alpha v lambda contains this single vector v lambda, so single vector v, and UGC of v is all of m lambda. So, the image, and so some holds, so the image of this is the whole of v lambda, whole of m lambda, and therefore, since this is made up of finite dimensional modules, so is this. Hence, the same holds, that is m lambda is a sum of finite dimensional SL2 modules. And that means you look at E minus alpha. On any finite dimensional module, E minus alpha acts nilpotently. We know all the finite dimensional modules. Every module is a sum of irreducible finite dimensional modules. On every irreducible finite dimensional module, we know it operates nilpotently. So, E minus alpha acts nilpotently on every finite dimensional SL2 submodule of m lambda. And since m lambda is sum of all the finite dimensional modules, SL2 modules, this implies E minus alpha acts locally nilpotently, is locally nilpotent on m lambda. And this is true for any simple root alpha. So, for every simple root, E minus alpha acts nilpotently, and so does E alpha, because E alpha again acts nilpotently on every finite dimensional module. So, what you have now done is to prove that.
You are using the structure of UG as a add action.
Sorry?
In this proof, you are using the action of G on UG not by.
No, but the adjoint action.
But the adjoint action.
I have said it here.
Is becoming important where? I mean, somehow the fact that it is direct sum of finite dimensional G module.
Yeah.
Is perhaps what is the region.
This is a finite dimensional sum of finite dimensional modules. So, each UPG is finite dimensional. Each UPGC is finite dimensional.
Yes. So that's
and it is a union of, it is a sum of all the UPGCs.
Multiply with the left regular projection.
So this becomes so this here therefore becomes sum of finite dimensional modules over SL2, this tensor product, because I have taken here the finite submodule, and if you look at the image contains UGC operating on V, and that is the whole of m lambda, because m lambda is irreducible. There is a vector V here sitting. So the image contains UGC on V, which is the whole of m lambda. So the mapping is subjectively onto m lambda. So, and it maps.
Typically, one would have taken the left multiplication, but it is the left multiplication, but you are treating this not as a left UG module, but as a adjoint action.
Right. The point is that when you
something there.
no, the point is that when you the tensor product, you can the point is that let me see, you can form two things, UGC tensor m lambda over, you treat this as a right UGC module and treat this as left UGC module, then you can form the product UGC like this. Okay, that's it turns out, and when you do that, and
This is not what you are doing.
no, this gives you back UGC m lambda. That's what I'm saying. If you take the on this UGC acts on the left, and this gives you m lambda as a UGC module.
Yes, because it's a free module, and you.
And then I'm looking at UGC tensor m lambda over C. Passing this, see what I'm happening is that left multiplication by UGC here is same as right multiplication on this side here, and that is why you have to, if you take this thing with the add as the representation, then what you get is a UGC module homomorphism. If you like, mappings like this, and this entire diagram is commutative. That's the reason it works. Okay, now this once you know that in SL2 you have the following formula. You look at the x puff look at this product. Notice this is nothing but, if I call this thing x, is just 1 plus x, because x square is 0 in SL2. Okay, call this element. It turns out that this element is nothing but 0 1 minus 1 0. It's a while group element. So the element S alpha, the reflection x alpha can be, sorry, reflection S alpha is the same as exponential of E alpha E minus alpha. Exponential this is a simple calculation. I may be off by sign, but it does not matter. It could be minus 1 1. Okay, reflection x alpha becomes this. But then if you do so, you find in any finite dimensional representation rho of SL2C, the 3-dimensional algebra, you find that rho of S alpha is equal to rho dot E alpha times, sorry, rho dot xp alpha times T minus alpha, rho dot x of minus E alpha times rho dot, so rho of, sorry, is equal to rho of x puff E alpha. But notice that these are nothing but sigma, each of this is nothing but rho dot, the corresponding representation of the Lie algebra, E minus alpha or k by k factorial is a finite sum, but I will try to k equals 0 to infinity because I do not know what dimensional representation I am looking at. So it can be, the dimension can vary. Whatever representation I have, I can write it like this, and then again the same term here. That is what rho S alpha equals. And then in a finite dimensional representation, you know that the rho S alpha will take one weight space into another. Okay. Therefore, you find that the conclusion is that any one of these, for alpha simple, rho S alpha permutes the eigenspaces of Tc in m lambda, and hence the eigenvalues as well. Eigencharacters, that is weights. So, in other words, we have an action of the while group on the set of weights of the representation. Once you have S alpha acting on it, you can compose S alpha as beta, etc. How does it operate on weights? It operates as it would operate on the dual of Tc. It operates on Tc, it operates on the dual of Tc, and that is how it gets on the weights. So, you find that get action of W on the set of weights. You have action of these reflections with respect to simple roots, but they generate the entire while group, as we know. That is why you get an action of W on the set of weights of m lambda. Suppose you have a, let mu be a weight of m lambda. Then I can look at all the weights W mu, W and W. They are all weights of m lambda. Let W naught mu equal to, say, mu 1 be the highest of these. Then if you look at notice they are all integral weights, they all take integral values on the H alpha, say alpha simple. So, W naught mu equal to mu 1 be the highest weight. Then we know that mu 1, first of all I want to say that mu 1 is dominant, that is mu alpha is greater than equal to 0 for every alpha. It is of course already integral for every alpha in pi. Why is this? Because if you look at S alpha mu 1, this is one of these weights, because I have simply W naught mu is mu 1 S alpha mu 1 is S alpha W naught mu. So, some other Weyl group transform of that. Okay. This has to be less than, because mu 1 be the highest of these, so this is less than mu 1. But this on the other hand is mu 1 minus 2 mu 1 alpha by definition of the reflection operation alpha alpha into alpha. Alpha is simple, this becomes mu 1 minus this. If this has to be less than this, but this is less than mu, and that can happen only if this coefficient here is with a minus sign here, so this only if this is positive. So that proves that mu 1 alpha is greater than or equal to 0. So this mu 1 is dominant, and we know something else. In m lambda, every weight is the form lambda minus some positive integral combination of simple roots. We know that. So what you find is this. We know that mu 1 is necessarily the form lambda minus sigma a alpha 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 in pi a alpha integers greater than or equal to 0. Now let us calculate, or equivalently lambda equal to mu 1 plus sigma a alpha alpha. Now let us look at what is lambda lambda. A alpha are non-negative, mu 1 alpha is greater than or equal to 0 as we have just now seen, and all these terms, this term is also greater than 0. With the inner product is, we know, on weights which take real values on HR, we know that this is positive definite. So you find that lambda lambda is mu 1 plus this is positive, this is positive. So we find lambda lambda in effect is greater than or equal to mu. Sorry, greater than or equal to mu, and which is also equal to mu 1, which is also equal to the original mu we started off with, because W naught preserves the inner product. So this is mu 1 is W naught mu. So all the weights are of norm less than or equal to lambda, but they are also integral, which means they belong to a lattice, and all of them are bounded by some fixed lambda lambda, which means there are only finitely many possibilities. So there are only finitely many weights. Number of weights in m lambda are finite. Moreover, if you fix one weight, suppose mu is a weight, then mu I know is of the form lambda minus sigma m alpha 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 in pi. But any weight vector comes from mu, a weight vector mu is a linear combination of the form lambda minus sigma a weight vector is of the form E alpha 1 E minus phi 1 E minus phi 2 E minus phi q of the vector V, the highest weight vector, right, phi r, which implies among other things we know that phi 1 plus phi 2 etc. plus phi r is of the form sigma m alpha alpha. There are only finitely many possibilities for mu. So but if you want this sum phi 1 plus phi 2 plus phi r to be sigma m alpha alpha with fixed m alphas, there are only finitely many possibilities for phi 1, okay, for the phi I. So that shows there are only finite, the weight spaces themselves are finite dimensional, implies all weight spaces are finite dimensional, and there are only finitely many weights. We have seen that here, and so it follows that this here, we seem to have erased it, plus the fact that there are only finitely many weights implies m lambda is finite dimension. This is the correct proof for the finite dimensionality. Yeah.
Why their angular bracket mu1 is same as mu? What is the
The while group preserves the inner product. See, if you look at the compact group, it preserves the inner product of the whole thing, which is negative definite, and therefore the corresponding positive definite inner product is also, I mean, the positive definite inner product is nothing but on H itself, on it, see, on the Lie algebra of the torus, it is negative definite, the killing form. So on the dual, the killing form is positive definite, and not on the dual on I times t, killing form is positive definite, and what we are looking at is the dual of I times t, because I am looking at those which take only real values, okay, on the H alphas. So it is positive definite, and the while group preserves the inner product.
and from there how do you conclude number of weights is finite?
No, see, these are all, if you look upon them as linear forms which take integral values on 2H alpha by alpha alpha. So they all belong to a lattice, okay. Once they belong to a lattice, the number of lattice points in a sphere, in a ball is finite in number. So that is why the number of weights is finite, because every weight is of norm less than or equal to lambda lambda. Every weight is of norm less than or equal to weight of norm of lambda, which is fixed for them. So there are only that means there are only finitely many weights, and each weight space is finite dimensional, because when you apply, how do you get weight space? The only way you can get the weight space is like this. And if you want to get into the weight space corresponding to the lambda minus sigma m alpha alpha, you will need phi 1 plus phi 2 phi r to be equal to m sigma m alpha alpha, okay. And there are only finitely many possibilities. These are all positive roots, and alpha are simple roots. So when you do this, there are only finitely many possibilities, and so you find that there are only finitely many each weight space is finite dimensional, and there are only finitely many weight possibilities, and so the entire m lambda is finite dimensional. This is the correct proof. Just ignore the proof given last time, except in the beginning I made some correct statements. Yeah.
Did we use that with the local nilpotence, or perhaps this?
Yeah, no. See, the local nilpotence is equivalent to saying it's a sum of finite dimensional representations. The two can be used interchangeably.
No, but this idea or this argument.
So the point is, if you have an infinite dimensional representation, there is no action of the while group. In principle, the while group comes from the group. The while elements in the while group come from the group. The group itself, I do not know if it acts. It's only the Lie algebra which acts. So if I want to get an action of the while group, I have to do some work for that. How do I do that? Suppose I knew that the whole thing is a sum of finite dimensional representations. Each finite dimensional representation integrates to a representative of the group, and therefore the compact simply connected group, and therefore the while group element
Nilpotence is used to construct the action of W.
of the while group, that the while group operates, comes from the fact that every representation finite dimensional. The nilpotence is guaranteed by the fact it's finite. It's a sum of finite dimensional representation, And I to give explicitly how the fact that it is nilpotent enables you to define a while group element is how I wrote down the Chevalier relation, that is lower triangular times upper triangular times lower triangular, the product is the while group element. So, m lambda is finite dimensional if 2 lambda alpha alpha are all integers greater than or equal to 0, that is what last time. And then last time I also stated a theorem for which I did not give a proof. I said I will give the proof next time. The following theorem is the following: let delta let rho be equal to half the sum of all the positive roots. Sum of all the positive roots I take and take half of that. I will presently say something more about rho. Then, in fact, I have to say 2 rho alpha by alpha alpha equals 1 for every alpha in pi. Secondly, and any element of A t this is, I don't know if this is notation I used last time, by which I mean the following: it's is of the form, sorry, let delta be the sum epsilon w rho, w is the while group. Epsilon w is determinant of w acting on t, or for that matter Tc, epsilon sub w. Then every function f in C of t, which by definition is the group algebra of C xt. Xt is the group of characters on T, and Cxt, each character is a function on T, and every element of Xt is therefore a function. And notice that this Xt is stable under multiplication. If you multiply 2 characters, you get another character. Though usually I am writing this Xt additively, but if you write it multiplicatively, it is clear that you can identify this with a certain algebra of functions. Algebra of complex valued functions on T, and I denoted by At. I hope this is the notation I used last time. At is by definition the set of f in Ct. The while group operates on T and therefore operates on the group algebra of T, which is group algebra Xt, which is what I call Ct. At is by definition set of f in Ct, Wf equal to epsilon W f, and St equals f in Ct Wf equals f. For every W in W. So, that is the definition of AT and ST, and last time I wrote down the following theorem. AT equals oh dear, times delta, where delta is this function here. Delta is treated as a function on T. Each of these things are characters on T, so linear combination is a function on T. Now, it is clear that ST times delta is obviously contained in AT, because if you look at function u here and delta, apply the while group element, it is same as WU W delta, but WU is my epsilon WU and W delta is delta. Oh, sorry, WU is U. WU is U, there is no epsilon W, and this is epsilon W times delta. So, that is clearly WU delta is same thing as epsilon W U delta, therefore, it belongs to AT. So, that multiplication by delta lands ST in AT is clear. I want to say it is onto. Why is this onto? The way you prove this is the following. Firstly, I can identify AT the following fashion. AT is the span of sigma is a C-linear span of W in W. Let me write 1 over mod W of epsilon sigma lambda dominant. See, I want to claim that lambda this AT is spanned by all such things. That is, I take a dominant character and then do this kind of averaging of lambda. This will land you, obviously this lands you in AT, that is obvious. So, apply another element tau epsilon sigma, tau sigma lambda is what you are going to get, and then if I apply to that, then I can write it as epsilon tau times epsilon tau epsilon sigma, which is same thing as epsilon sigma tau, and there is tau sigma or epsilon, which is same thing as epsilon tau sigma, and here you get tau sigma lambda. Sigma varies over W, tau sigma also varies over W. So, you get the same summation, except now get epsilon tau as an extra factor. So, that shows that this belongs to epsilon tau. So, what we are doing is take the entire group algebra, the entire CT we know is a linear combination of various weights. Okay. Now, notice that if mu is any weight, is any character on T, then and mu naught is the dominant character. We have seen that there is only one dominant character in any wild group orbit. I fix a mu and then you take the wild group orbit of that, you get various characters, and there is the largest of them, and the largest we have seen already is a dominant character. So, mu naught is a dominant character in the W orbit of T. Then we see that 1 over mod W sigma W in W epsilon sigma lambda is same as sigma W in W in W epsilon sigma. So this is epsilon W W mu naught. Sorry, it's a epsilon let me write sigma, where mu naught is sigma mu. Okay. Whether I average, whether I operate W and then average with this factor epsilon W, whether I take mu naught or mu, it's the same, because we know that mu naught is some sigma mu. So I can replace this by W sigma mu, which means I can also write here in the summation, I can write W sigma and take out an epsilon sigma, which shows that this happens. So the linear span of this, as lambda varies over dominant weights, is the same as the linear span of this over all weights, all characters. Instead of, I don't have to, if I take all characters or with the dominant characters, I get the same summation. Okay. So AT is equal to this. So to prove our theorem, we need only show that each one of these, we just have to show, so it suffices to show that for every dominant lambda, this average sigma epsilon sigma lambda sigma in W belongs to ST times delta. Yeah, this is what we need to prove. We will do it by induction. Start the induction with, notice, yeah, we will do this by induction the following fashion, that is, proof by induction of the order on dominant weights. So suppose we have proved this for all dominant weights. Suppose this shown for all lambda strictly less than lambda. So we have a total order. We are working with a total order, and then we want to see if it's true for all lambda less than lambda. I want to prove it for lambda as well.
Total order?
There's a total order. On the linear forms, I introduce a total order. And one alpha is less than beta. If you fix a basis and This is lexicographic order which you introduced.
So it is not by summation ki alpha I.
Hmm?
It is not by the earlier relation summation ki alpha I where ki are positive.
No, that's a partial order.
Yeah, that's a partial order.
The total order, there's a total, one starts with total order, and then from that of course you get simple roots are defined using a total order, okay, and then you can introduce a partial order by saying 2, then if it's a partial order you cannot compare, and then it becomes more complicated to do the induction.
So can you define the partial order again, total order?
Fix a basis h1, h2, hl of the I times k, and you say lambda is greater than 0 if the first non-vanishing lambda hi is greater than 0, the so called lexicographic ordering.
You will fix an ordering also.
No, see, fix a base on any vector space.
Fix an ordering on the.
Take a real vector space V and basis, ordered basis E1, E2, ER. I will say alpha in V star is greater than 0 if the first non-vanishing alpha EI is greater than 0. That gives you a total order. It's so called lexicographic ordering. Okay, and that's what I've been working with all the time. Lexicographic ordering is what I've been using all the time. The fact that
Summation ki alpha I where ki is positive, I thought is what was being.
no, if
previous
you
argument.
see the first non-zero Ti positive is the total order. If all the Ti are positive, you get only a partial order. Okay, that's the way it works. Okay, now where was I? The first remark I want to make is the following: if lambda dominant is such that lambda minus lambda on 2 lambda alpha where alpha is 0 for some alpha in pi. If this happens, then our averaging process w lambda epsilon w lambda lands you in 0. Why? Because I can write this as 1 over mod w and then sigma w in w mod the group of order 2 generated by S alpha, and then here I write as epsilon w S alpha lambda minus lambda. You see, W S alpha has to be multiplied by epsilon W S alpha, but epsilon S alpha is minus 1 and epsilon W is already here. So, this summation is same as this, where I have chosen this means a set of representatives for the W is in this means I am choosing a set of representatives for these cosets, for this coset classes. But notice that S alpha lambda, epsilon W is W lambda should be, okay. That is how it gets written. Now, notice that S alpha lambda minus lambda is 0, because this is nothing but lambda minus 2 lambda alpha by alpha alpha times lambda, but this is 0. So, S alpha lambda is same as lambda because of our assumption that 2 lambda alpha by alpha alpha is 0, and therefore, this is 0. So, the whole thing sum is 0. Okay. So, we can start the induction. Lambda is we are only looking at the dominant lambda, and one of those dominant, if if lambda alpha is greater than 0, it is not the smallest possible. If lambda alpha is greater than or equal to 0, it is not the smallest possible element. There are lambdas such that lambda alpha is 0. So, there will be something smaller because of that. Notice that if lambda is greater than mu in the partial order in what you said, then automatically true it is greater than 0 in the total order. Okay, now, so let me suppose now we have proved the statement when lambda assume statement holds for all lambda dominant and less than lambda. Then I want to prove the same thing is true for lambda. What do I do for this? Firstly, note that if I
The statement being the subjectivity of the map. The statement being
is a subjectivity of the map, yes, right, on to it. In other words, yeah, but so I look at A, let me call it A lambda sigma epsilon sigma now. Firstly, I want to note that this is orthogonal to 1 over W sigma and W epsilon sigma lambda for all lambda dominant and less than lambda. This is because if you look at each of these characters is orthogonal to each of these characters. The dominant character, lambda is dominant and lambda is greater than small lambda is the dominant, and the two cannot be in the same Weyl group orbit. In any Weyl group orbit there is only one dominant weight. If lambda is dominant and less than lambda, it cannot be equal to lambda, and any two characters on a torus, distinct characters of torus, are mutually orthogonal. So, and nothing in the Weyl group orbit of 1 lies in the Weyl group orbit of lambda. So, they are all orthogonal to each other. So, this implies, so A lambda is orthogonal to all the elements. And then all the A lambda coming from the earlier ones. So, all the earlier ones we have shown. On the other hand, this if orthogonal to A lambda. We have already claimed that A lambda is already contained in delta times S t, in fact I can say it is contained in delta times we know that A lambda is already contained in delta S t by induction hypothesis. Delta, remember, is nothing but AF rho. Yeah. Notice that the A lambda, as lambda varies over lambda dominant, this collection is a basis for A t and are all mutually orthogonal. And this is the whole of their span is therefore is A t. Right. Now I am looking at, I want to prove next that A lambda is also delta of S t. Yeah. What's happened now? This is the average sigma in W. This one is 1 over W epsilon sigma rho sigma in W. I'm a bit confused now. This is yeah. If I now look at the lambda sigma of this, oh yes, yeah. Right. I must also say can assume lambda 2 lambda alpha by alpha alpha is greater than or equal to 0. Is an integer strictly greater than 0 for every alpha pi. Because we have seen if it's 0, then the average is 0. There's nothing to prove. Since A lambda is 0, if this is not satisfied. And therefore, it follows that in fact this implies that lambda minus rho is dominant. Okay, now let us look at yeah, so lambda itself mu plus rho, mu dominant. Now let us look at the symmetrized mu. S mu equals S of sigma and W, sigma mu, average of mu without the epsilon sigma factor. This belongs to ST clearly. And let us see what happens to, so AF lambda is AF mu plus rho which is, now let us compare this with S mu times A rho, which is delta. Let us look at this on the one hand. A lambda, which is A mu plus rho, and look at this on the other hand. Now you see the weights occurring in S mu A rho, when you expand it out, includes mu plus rho. The dominant weight mu will see S mu is sum of sigma mu, and A rho will have S mu, it contains mu, and A rho starts off with rho. This is averaging over, so mu times rho will occur there, mu plus rho will occur there, and that is, it is the maximum weights occurring in this and no higher weights. Okay. It is true on the left hand side as well, because it is dominant, you get only lower weights than start with mu plus rho and you get only lower weights. So you find that the two are not the inner product is not 0, because that does occur and others cancel out anyway. No, the inner product is not 0, which means this alternating sum contains something orthogonal to the earlier ones. Okay, not this alternate, this product contains something orthogonal to the earlier ones, and it certainly has, when you expand it out, it certainly is a combination which involves mu plus rho and all its conjugates. Because of that, this means this S mu times A rho will be a sum of lower alternatized forms, lower alternatized linear forms, and the present one. So it contains, therefore, this product is sum of some C lambda, A lambda, with lambda less than lambda, and plus some constant C times A lambda. That is the only extra thing that is coming up. So it proves this element is in the image of the symmetric. So the mapping is surjective, because the averaging process is a surjection on the alternating forms, because if you start with a thing which is already alternating and you apply this epsilon sigma lambda will become sigma lambda is already epsilon sigma lambda. If I start with a function which is sort, so AF equals F for every F in AT. The averaging process, I am applying it to characters, you can average it to apply it to any function, and then this happens if AF equals F for every F in AT, because F transforms under epsilon sigma when you apply sigma. So you find it, and then you get epsilon sigma square, which will become identity, etc. So you find that this is surjection onto all alternating things. Now we have shown inductively that every A lambda for lambda dominant belongs to the image. So the mapping is surjective onto alternating things. Okay. So yeah.
Maybe a good point to stop.
Hmm?
Time.
Sorry.
It's a good time to stop. I think.
Yeah, I think it's almost time to stop. I think this is a good point at which I'll stop. So next time I'll prove what is known as the wild character formula, which tells you how to write down the character given the dominant weight. And from that one can deduce what is known as the wild dimension formula, which tells you how to write down the dimension once you know the highest weight. So that's the last lecture, and I hope I won't make any mistakes and don't have to carry on one more lecture. So only one more lecture I have to give, and you have to tell me when I can do it. Today is 6th, okay. 20th then, Monday 20th, okay.